This is 3-7 day 2, and we're talking about implicit differentiation, and we're going to do a higher order derivative using the implicit methods. So implicit differentiation, just to kind of recap, is when it's really cumbersome to solve for y to do a traditional dy dx derivative. So getting this in terms of y equals, it's not terribly difficult, but once we do, it involves a square root, and then we have a radical, and then it gets messy. So instead, we developed this method called implicit differentiation, where we take the derivative just from left to right, and when we run into a y term, we use the chain rule, and then we solve for that dy dx. So that's the first step in here. We've got to use eventually we've got to use the quotient rule, but that question is a little out of order, I think. First thing we have to do is use implicit differentiation. So the derivative of 2x cubed is 6x squared. That's just a normal derivative since it's an x term. The y term here, we take the derivative like we would typically do the power rule. So bring down the 2, make it a 6. So this is a 6y. And then we have to do a chain rule here because this being a y term, this is the derivative with respect to y, and we need to do y dx. So we have multiply that by dy dx, or y prime. We can write that either way. I just chose the prime notation instead of the Leibniz notation. And then we have an equal to sign, and the derivative of 7 is 0. So now we can solve for this. So solving for this, we take the 6x squared to the other side. We divide by negative 6y, and I probably simplify this. There we go. So the derivative y prime, or dy dx, is x squared over y. And so I'm asking for the higher order derivative, the second derivative. And so if I want my second derivative, this is where I need to use the quotient rule. I think this was just a little out of order in its in how it popped up in the PowerPoint. So since I have this, I need to use the quotient rule. So now I need to do the low d high minus high d low over low squared. So low d high is going to be y times 2x minus high d low is going to be x squared, and derivative of the low is 1 times dy dx, or 1 times y prime, and that's all over y squared, which is the low squared. So here's the second derivative. This is a little problematic. If you notice, because we have an implicit expression, x's and y's mixed together, we have an implicit derivative, x's and y's listed together, and we also have an implicit second derivative, x's and y's all mixed together. But the one thing we do have to get rid of is this y prime. We can't have a derivative inside a derivative expression. So the first thing I'm going to do is split this into 2 fractions, because I can see some simplifying that can possibly go on here. So this is 2xy over y squared, which is just 2x over y, minus, and then I have x squared divided by y squared times y prime. And the reason why I wrote the second one like this is because I'm going to take this y prime out and put in its expression, x squared over y. So I'm going to substitute that out. And then I can do some simplifying on that second fraction. So this ends up being x to the 4th, and this ends up being y cubed. So the second derivative is this. So let's try this problem here. We're going to find the equations of the line tangent and normal to this curve at 0, 2. So this is an implicit expression because the x's and y's are all mixed up. And a lot of times we write this implicit form because we're dealing with a curve that's not a function. So we're usually dealing with like a conic or something that's not a function. So we're going to use implicit differentiation to differentiate this. So when we do implicit differentiation, we do derivatives with respect to x, just like we always would. We'll have to do a product rule here. When we take derivatives with respect to y, we'll have to follow that up with a dy dx for the chain rule. We could also follow that up with a y prime, because that means the same thing. So we know that we're going to have to use the product rule here for this portion. We're going to do this implicitly. We're going to call it y prime, though, instead of dy dx. It makes it look a little cleaner. Okay, so let's take the derivative of this. That's 2x. Now let's set ourselves up for the product rule here. So I'm going to type in minus 3, and then I'm going to put the product rule in here. So I'm going to do the derivative of x times y plus the derivative of y times, the derivative of y times x. Okay, so the derivative of x is 1 times y plus the derivative plus x times the derivative of y, which is 1 y prime, or 1 dy dx. And then I've got a plus here I'm going to put in, and then this derivative is 2y dy dx, or 2y y prime. And then I have an equal sign, and the derivative of 4 is 0. So I've done the implicit differentiation here, and now I just need to collect my y prime terms. Notice I have y in 2 locations, so I have y prime in 2 locations. I just have to collect these y prime terms. So now after this, it's all algebraic. So I'm going to distribute the minus 3 here. So I've got 2x minus 3y minus xy prime, minus 3xy prime, excuse me. And then I've got this term plus 2y y prime equals 0. Okay, so here are my y prime terms. I'm going to leave them here. I'm going to take these to the other side. So on the other side, I'm going to have a minus 2x and a plus 3y. So those are these two terms, and then equals 3y minus 2x. I'm going to factor out my y prime here. So when I do that, I'm going to be left with minus 3x plus 2y in brackets. And then I have the right-hand side here, and then I'm going to divide by this. And when I divide by this, and I also flip these terms just because it looks a little nicer. So here's my derivative. It's 3y minus 2x over 2y minus 3x. So if you notice, because we had an implicit form of our curve, we have an implicit form of the derivatives. We have x's and y's all mixed up, and that's okay. We just leave it like that. So there's the derivative. Now I want to evaluate that at 0, 2. In other words, I want to find the slope. Right? You say slope, you're thinking derivative. So if I plug in 0 for x and 2 for y, so here's the 2's, here are the 0's, and I do the math here, I get 6 over 4. And so 6 over 4 is 3 over 2. So the slope is 3 over 2. So this is the curve. So this curve, it looks like this. As you can see, it's not a function. Right? We do the vertical line test, it doesn't pass. This is a hyperbola, excuse me. Hyperbole is an English thing, I think. This is a hyperbola. Here's the point 0, 2. We know the derivative there is 3/2. That means the slope of the tangent line is 3/2, up 3 over 2. Okay, so there is, there's the slope, 3/2, and now I'm going to write the equation of the tangent line. So I'm going to put my slope over here, my x-coordinate, which is 0, my y-coordinate, which is 2, and I'm going to, okay, I did a little math here. I would have just left it like this. And there is that tangent line with the slope 3/2, up 3 over 2. Okay, so there's my tangent line. Now I'm going to do my normal line. Remember, my normal line is perpendicular, so it's going to come across right like this. So what that means is it looks exactly like this, but I'm going to have to take the opposite reciprocal here. So here's my opposite reciprocal. I get my same point slope form. I drop my slope in, drop my 0 in for my x-coordinate, drop my 2 in for my y-coordinate, and there's my normal line. I probably clean that up a little bit too. These last 2 steps here, doing the algebra to clean it up, are totally unnecessary. So there's my normal line, which has a slope of down 2, right 3. Okay, so let's use implicit differentiation to find the derivative of this. So interestingly enough, I graphed this over here. It's a series of little circles. So again, not a function, right? We do the vertical line test and we pass through several circles, several tops and bottoms of the circles as well. Or we could potentially pass through nothing. So we're going to need the product rule here, okay, because we have a cosine times a sine. We're also going to need a chain rule here. So we're going to need a couple of things. Okay, so let's start setting ourselves up here. We've got 7 times, and now we're going to do the product rule here along with the chain rule. So outside derivative is minus sine 2x. Remember, when we do the outside derivative, we leave the inside alone. And then we go times 2, because that's the derivative of the inside. So that's the derivative of the first, and then we have to go times the second, plus the first, and now we have to do the derivative of this. So it's going to be cosine 3y times 3. And then since that's derivative of a y term, it's times 3y prime. There's my derivative. So notice 1y in the implicit form, 1y prime in the implicit form. And then the derivative of 5 is 0. So let's take a look at what we did here before we go to the next step. This whole long thing is the product rule, right? Derivative of the first times the second plus the first times the derivative of the second. And then inside here we had to do a chain rule. So just to recap, this is the derivative of the cosine times the sine plus the cosine times the derivative of the sine. So derivative of the cosine is right here. And then using the chain rule, there's the derivative of the inside times the sine. So derivative of the cosine times the sine plus the cosine, that's unchanged, times the derivative of the sine. Derivative of the sine is the cosine. And then we have to take the derivative of the inside, which is a y term. So it's 3y prime. Okay, so I'm going to clean this up here a little bit. Oh yeah, I do clean this up here. So I have minus 2 sine 2x sine 3y. And I have plus 3 cosine 2x cosine 3y y prime. So I always hang the y primes over the end. And then it equals 0. So we lost the 7 here. So what we actually did here that I didn't put a step in is I actually divided each side by 7. And 0 divided by 7 is still 0. Okay, this is the y prime term. This is going to stay here. This term needs to be moved over to the other side. So that's going to become positive. And then I'm going to divide by 3 cosine 2x cosine 3y. So I'm going to divide by, okay, so this is where we were on the last page. So when I divide by 3 cosine 2x cosine 3y, I get this. This is the top, that's the bottom. So here's our derivative. And I don't think I asked for the slope, so we just, we're just leaving the derivative in that form. There's really no way we can simplify that. Oh, surprise. There is a way we can simplify it. We have sine of 2x over cosine of 2x. It's a tangent. Sine of 3y over cosine of 3y is also tangent. So we can actually simplify it. That looks a lot nicer than this. Okay, so this is a short discussion here. This is not in your notes. But this is kind of recapping the power rule in non-specific forms. So if we have x to a power, we know the power rule is to bring the power down and then multiply times x to the 1 less power. And that power rule can be used for any exponent except for -1. Okay, so, and that's kind of what this is saying here, but it's not saying it in friendly terms. Yeah, I'll just leave it at that. But this is just a recap of the power rule. So let's do this. Let's do a power rule with a power of pi. So we got to bring that pi down times x, and then 1 less. We could call it 2.14 if we wanted to use a decimal, but we could just leave it as pi minus 1. So we can do this for any power up here. With some slight restrictions. So just to summarize then, we were using implicit differentiation, and when do we need to use it? When we can't when we can't solve a function for y. That's when we need to use it. And a lot of times, if that's the case, it's because the expression is not really a function. I actually shouldn't even use the word function up here. So at this point, you should be able to do the day 2 homework for implicit differentiation. And this is the end of the section 3.7. So if you'd rather take the proficiency quiz to test out of the section, you could do that as well.